So the reason you want to be able to factor a polynomial is so that you can find the roots. And recall that the roots, that's the same as saying find the zeros, or the same as saying find the solutions, or the same as saying find the x-intercepts. So when we think about a polynomial might look like this, and we want to find the places where the curve crosses the x-axis. And one way to do that is by factoring and then using the zero product property. Recall that your zero product property says if you have two things multiplied together or more, two or more things multiplied together that equal 0, then A could equal 0 or B equals 0. So we're going to use that principle in order to find the roots of a polynomial. So here's our example. We have x cubed plus 7x squared minus 9x minus 63 equals 0. So just back when we were doing quadratics and solving them, same thing, the equation needs to be set equal to 0 to start with. So I'm going to start by factoring. First, how many terms are there? Or is there a GCF? There's no GCF. I recognize that there are 4 terms, so I'm going to factor this by grouping. I'm going to start by pairing the first 2 and factoring out a GCF of x squared. So I get x plus 7. Then I look at the second 2, and if I factor out a negative 9, I'll also get x plus 7. All that still equals 0. Recall, these two values are the same, so I'm going to factor them out into their own binomial. And then the leftovers would form their own binomial. But notice this binomial is a difference of 2 squares. So my final factored answer would be x plus 7, x minus 3, and x plus 3. And all of that's equal to 0. What that means is that each one of these binomials, each one of these is possibly 0. So I can take each of those and set them equal to 0. And x plus 3 equals 0. And then I solve each of those statements. In this case, x is going to be negative 7. X would equal positive 3, and x would equal negative 3. Therefore, our solution set contains 3 numbers, negative 7, negative 3, and 3. And that's how we find the solutions by factoring. All right, let's do another example. So here we have 4t to the 6th minus 20t to the 4th plus 24t squared, and all of that is already equal to 0. So the first thing I'm going to do is factor it, or try and factor it. Is there a GCF? There is. The GCF is 4t squared. So if I take that out, I'm left with t to the 4th minus 5t squared plus 6, and all that equals 0. This trinomial, I want to see if it's factorable. It's a little weird because it's t to the 4th, but notice it just follows the same form. Like if we had x squared minus 5x plus 6, you could factor that, and the x would just factor into x and x. So here, this is now just going to factor into t squared and t squared. Okay, so we have 4t squared. Then we'll have one parentheses that's a t squared, another parentheses that's a t squared, and then I need factors of 6 that will combine in a way to give me negative 5. So I need the signs to be both negative. So this ends up being 2 and 3. Those are the only ways that I will get 5. And then now these are all equal to 0, so each one of these things I can set equal to 0. So 4t squared equals 0, t squared minus 2 equals 0, t squared minus 3 equals 0. And I have to solve each one of those. Here, if I divide by 4 on both sides, I still get t squared equals 0. Square root both sides, I still get t equals 0. I'm going to subtract 2, so I get t squared equals 2. And then I square root both sides, and I get t equals plus or minus the square root of 2. I'm going to subtract 3 to get t squared equals 3, square root both sides, and I get t equals plus or minus the square root of 3. So this solution set now contains actually 5 different solutions. So we've got 0, we have plus or minus the square root of 2, and plus or minus the square root of 3. And those are all of the solutions for this equation. That's how you use a zero product property to solve.